Hello students, welcome to another session on electric field intensity. So today's class will be revising what we have learned in the last class first. So we have studied the expression for electric field intensity vector E as 1 by 4 pi epsilon 0 q divided by r square a r cap if the charge is kept at the origin and we are assessing the electric field intensity at a distance r from the origin. And the direction of the electric field intensity is along the radius, so AR cap will be the. So this is in the case of spherical, and we have transformed this into the uh, Cartesian coordinate system, and we found that if the system is at the origin and the location where you want to find the uh, electric field intensity has the coordinate x, y, z, then it is given by q divided by x square plus y square plus z square whole raised to 3 by 2 into x ax cap plus y ay cap plus z az cap. And also we have uh, seen the electric field intensity expression for electric field intensity if the point charge where the charge and the point at which you want to assess are at different point. If the charge q is kept at x dash y dash z dash and the unit vector for the position vector for this is r dash and this is r, then the expression for electric field intensity is obtained by 1 by 4 pi epsilon 0 q divided by into q divided by mod r minus r dash whole cube into vector r minus r dash. So the cube term comes because you are finding the unit vector along this direction, that also we have to divide it by its magnitude, or we can generalize it as 1 by 4 pi epsilon 0 q into x minus x dash ax cap plus y minus y dash ay cap plus z minus z dash az cap divided by x minus x dash square plus y minus y dash square plus z minus z dash square whole raised to 3 by 2. So to the power 3 by 2 is like finding the square root first and then finding the cube. So these are the things we have studied in the last class. Today we will be discussing about electric field due to a system of charges. If more than one or you have a charge like a q1 here and you have a charge q2 here and you have charge q3 here, or similarly you have many charges like a q4 q5 etc. qn charges are there. Then if you want to find electric field intensity at a point here I am considering as a point P. Let be this the position vector of this one, let it be r1, then position vector of this, let it be r2, this is r3, r4, that is the vector connecting origin and that point. This is r3, this is r4, this is r5, and this point is a arbitrary point, the vector is r. Then field due to q1 is denoted by E1 is equal to 1 by 4 pi epsilon 0 q1 divided by mod r minus r1 whole cube into r minus r1. Similarly E2 is equal to 1 by 4 pi epsilon 0 q2 divided by r minus r1 cube r2 cube into r minus r2 etc. For same all the electric field intensity can be calculated, and total electric field is E1 plus E2 plus etc. up to En. So we will do a problem, we will clearly understand how it can be done. So the question is given as find E at a point and 1 comma 1 comma 1 caused by four identical 3 nanocoulomb. So identical 3 nanocoulomb means all are having same magnitude and same charge, that is either positive or negative. Since it is 3 nanocoulomb, it will be positive only. Charges located at P1 1 comma 1 comma 0, P2 minus 1 comma 1 comma 0, P3 minus 1 comma minus 1 comma 0, and P4 1 comma minus 1 comma 0. You can represent this as a diagram with the four coordinates P1, P2, P3 and P4. You want to find somewhere here, because these are having z-axis component as 0, and this comes in the middle of this, which is little bit upper, having a z-axis component 1. So we have to calculate electric field intensity due to all these charges and add them up. So we will do that. So what I want is the vector r. Vector r is the position vector of this point, that is nothing but 1 1 1. So that is x is 1, y is 1, z is 1. So I can write ax cap plus ay cap plus az cap. Okay. Now we can write r1. So what is r1? R1 is this vector P1110, so it will be ax cap plus ay cap plus a0. So what is mod r minus r1? Mod r minus r1 will be, so what is vector r minus r1? So 1 minus 1, 1 minus 1 will be cancelled, only az cap you have, and modulus of r minus r1 is equal to square root of 0 square plus 0 square plus 1 square, that will be root of 1 equal to 1. Okay, that we got. Now what is r2? Vector r2 is minus ax plus ay. So if you subtract r minus r2, so what is r minus r2? Is nothing but ax minus minus ax, so 2ax cap plus ay minus ay will cancel, az minus 0 az, so az cap. Mod r minus r2 will be square root of 2 square plus 1 square, so root 5. Similarly, we have to find the third one. So what is the third one? I'll erase this diagram. So third one is r3. Vector r3 is minus ax cap minus ay cap. So if you subtract r minus r3, so what is r minus r3? ax minus minus ax, so 2ax cap, ay minus minus ay, so plus 2ay cap plus az minus 0, so az cap, and the value mod r minus r3 is square root of 4 plus 1, so 3, root 9. that is nothing but 3. And the last one, r minus r4. R4 is how much? 1 minus 1, so ax cap minus ay cap. So r minus r4, vector r minus r4 is nothing but 0 ay, so 2 ay cap, ay minus minus ay, so 2 ay cap plus az. So mod r minus r4 is nothing but square root of 2 square plus 1 square will be root 5. Okay, so this is how we calculated the value of r, r1, r2, r3. Now we will calculate the electric field intensity. E1 is nothing but 1 by 4 pi epsilon 0 q1 divided by mod r minus r1 cube into r minus r1. Similarly, E2 is equal to 1 by 4 pi epsilon 0 q2 divided by mod r minus r2 cube into r minus r2. So similarly, you can write up to E4, which is 1 by 4 pi epsilon 0 q4 divided by mod r minus r4 cube into r minus r4. Here we know that q1, q2, q3 and q4 are identical. So all these charges and 1 by 4 pi epsilon is common when you write the total electric field, which is E1 plus E2 plus E3 plus E4, where all these 4 terms contains 1 by 4 pi epsilon 0, and q1, q2, q3, q4 all are equal, so I can take it as a q, that is nothing but 3 nanocoulomb, into the remaining changes are here, vector r minus r1 divided by mod r minus r1 cube plus r minus r2 divided by mod r minus r2 cube plus r minus r3 divided by mod r minus r3 cube plus r minus r4 divided by mod r minus r4 cube. So if you add all these values, so what you will get, 1 by 4 pi epsilon is 9 into 10 raised to 9, 3 nanocoulomb is 3 into 10 raised to minus 9 into, we'll add all these terms. So r minus r1 is az cap divided by 1. So az cap divided by 1 cube plus next term r minus r2. So r minus r2 is 2ax cap plus az cap divided by root 5 cube. So 2ax cap plus az cap. So 2ax cap plus az cap divided by root 5 ka cube plus r minus r3. R minus r3 is 2ax cap plus 2az ay cap plus az cap divided by 3. So 2 to 1. 2ax cap plus 2ay cap plus az cap divided by 3 cube plus, and the last term is r minus r4, which is 2ay cap plus az cap divided by root 5 cube. 2ay cap plus az cap divided by root 5 cube. So you can add all of them together and find the final value. So it will be 9 into 10 raised to 9. This will be 27 into az cap by 1 plus 2 by 5 root 5 az by 5 root 5 to ax by. So you have to add all these terms az, az here and az here. So if you add all of them and simplify the expression, you will get as 32 multiply with the 27, you will get 32.8 a z cap. Similarly, you have 2 by 5 root 5 and 2 by 9 uh, into 27. If you simplify that, you will get 6.82 ax cap. And the third term is ay cap. So 2 by 9 plus 2 by 5 root 5 into 27, it will be again same expression 6.82. So ay cap. So this is the final expression for E. Okay, this is how you have to solve field due to system of charges. Okay, moving into field due to continuous volume charge distribution. So we will discuss first what is volume charge density. So volume charge density is nothing but it is represented as rho v. So rho v is nothing but delta q by delta t. Now why we are discussing about volume charge density? In the previous case we have discussed the case of charges which are system of charges. We call it a system of charges. This is separate entity, this is separate entity, this is separate entity, this is separate entity. But in real cases these cases are rare, but in real cases we may have a volume like this and it is filled with the charges which are very close to each other, and we call this as a volume charge. Okay, so we have to calculate the field due to this volume charge. So in that case we will consider a small element of this one, we call this as a dv, okay, or delta v. So at a delta v there will be some charge that is called delta q. Okay, so we don't know the value of delta v, we don't know the value of delta q, but for this entire charge there will be charge density which will be measured experimentally. Okay, we cannot measure the charge at a particular point, but we can measure experimentally charge density, which is denoted as delta q divided by delta v as limit delta v tends to 0. Okay, so I can write it as rho v is equal to dq by dv, or dq is equal to rho v dv, or q is equal to integral over volume rho v d. So we have to discuss about this integration first, and later once you find the value of dq we can calculate the value of E. Okay, so that is different case. Now we will discuss about how to find the volume integral in different coordinate systems. So first we will discuss about Cartesian coordinate system. Then in that one I am considering a small element, volume element dv. Then it is Cartesian rectangular, so this piece will be rectangular and you know all the components. So this is, what is this component? This is along the x-axis, right? So this is the dx, this is along the y-axis, this is along the y-axis or dy, and this is perpendicular, so this is dz. So what is dv? dv is the product of these three, that will be dx into dy into dz. So our volume integral q will be integral over volume function, that is rho v dv. So we know that it is integral over volume rho v dx dy dz, since dv is dx dy dz. So we know that there are three variables. So our integration will be, uh, see here, the V should be small letter v representing volume, because in our later chapters we will be discussing potential, which is representing capital V. So since there are three variables, so I have to use a triple integral. The first one along over x, second one over y, and the third one over z. Normally we will do this integral first, then the second integral, then the third integral. We will see examples later. Okay, this is in the case of Cartesian coordinate system. Now what is in the case of cylindrical coordinate system? So if I zoom this portion, this will be a piece of cake like this. So it is not actually rectangular box, but we have to approximate this as a rectangular box, and this is rho. So in that one, a small element is represented as d rho, and this is z. This is z. So in that one small piece. So this is this. Now what about this length or this length? Okay. Now this is nothing but a arc of a circle. Now you know that in a circle, if this is the center and this is the angle theta and this is radius, then the length of the arc is obtained by arc is equal to r into theta. So we'll apply the same principle here. We know that this is rho and this is a small piece in the angle, so we'll call it as d phi, because our this angle is actually phi angle, right? In that one, a small element represents d phi. So you know radius, that is rho, and angle is d phi, so this will be rho into d phi. So we approximate this as a cube now instead of that, but we got the dimensions and approximate. This is a d rho, perpendicular is dz, and this length is rho d rho. You may have a doubt why I am not taking the inter one, but we are just approximating because we are assuming this is very small such that I can neglect all those changes. So so what is dv, the volume of that small element? So length into breadth into height, so that will be rho d rho d phi dz. Remember this, there is an extra term rho d rho, so that comes due to rho d phi here. Okay, so rho d phi dz. So this is in the case of cylindrical coordinate system. I'll go for the next one, that is the spherical coordinate system. In the spherical coordinate system, I have, this is the direction of r, so a small piece in that one will be dr. Okay, so this is the piece which I take from a sphere. So I got this length, that is nothing but dr. And what is this angle which is made with the z axis is nothing but d theta. And what is the radius? R. So what is this length? This length will be radius into angle, so that will be r d theta. So dr r d theta. So now we want the third parameter. So this one that I cannot find directly because I don't know what is this angle, because it is vertically up. So I am projecting that point down below, which will be a piece of circle or a sector of circle. So this angle which is in that plane, we know phi. In that one, a small element means a d phi, and we should know what is this radius. It will not be r. This length will not be r because this is just a projection. So we know that this angle is theta. So opposite side of opposite component will be sin theta component. So this I can write as r sin theta. So what is arc length now? Radius into I will erase here. So this length is r d theta, and here it is arc is equal to radius into angle. So radius is r sin theta. Remember why r sin theta? Because this is not the length. I have to project that to the xy plane, so that will be projected. So it will be like this is r now. This is the angle theta. The projection of this one I want. So this length will be sin theta is opposite divided by hypotenuse, that is this divided by r is equal to sin theta. So this will be r sin theta, that is what. So radius is r sin theta into angle is d phi. Okay. So we got an approximate cube with the length, height, width as follows. So this is dr, and the height is this height is r d theta, and this width is r sin theta d phi. So what is dv? dv is equal to the product of all these, so that will be r square sin theta dr d theta d phi, d theta d phi. Okay, r square sin theta dr d theta d phi. Remember this expression also. So we can summarize as follows: dv in Cartesian it is dx dy dz. In cylindrical it is rho d rho d phi dz, and in spherical it will be r square sin theta dr d theta d phi. So this is the expression for dv, different coordinate system. So why this is required? We have to calculate the value of q, which is nothing but rho v dv. So this is a triple integral. In the case of Cartesian, it will be integral over x, integral over y, integral over z, rho v into dz, because I am writing dz first, then dy, then dx. Similarly here it will be integral over, reverse order I will go, z phi rho, rho v into rho d rho d phi dz. Please always don't confuse this rho v with this rho. This is the rho of cylindrical coordinate system. This rho v is volume charge density. Okay, so there is a difference. So same in the case of triple integral. In the case of spherical, it will be from this one r pi theta and phi rho v r square sin theta d dr d theta d phi. So this is all about today's class. We will discuss how to find the volume charge density in the next class. Till then, bye, thank you.